Hello, everyone, and welcome back to another episode of Solidity Fridays. Today, we will be looking at how to architect a zero-knowledge application, and I'm joined by a special friend, Danish Shabbir. Danish, how are you doing?
I'm well. Thanks for having me, Tam.
Yeah, thanks for joining. So Danish is very interested in zero-knowledge, as am I, and we thought we could maybe talk about the architecture of a zero-knowledge application because they often involve Solidity verifiers on chain, so it can still feature on Solidity Fridays. And this on the screen is the basic components that will go into zero knowledge application. Dinesh, do you want to walk us through it?
Yes, and just a little higher level note. I've been trying to read up on and develop my expertise in ZK and always end up in exotic mathematics. So I was really curious to take this approach and unpack some indie projects to see how you can build ZK apps with the primitives and libraries that are available today. So as we look through these projects, it's helpful to have this bigger picture in mind of all the elements that are involved. Tam, are we presupposing some knowledge of what ZK proofs are?
Yes. So I made a workshop on Solidity Fridays a few weeks ago that outlined just the basics of zero knowledge proofs. It was very similar to what I did at eSafari that Talkie attended, that workshop.
Yes.
So let's assume that people know that much already.
Great. So let's assume you're trying to build an app and you want to make some use of zero knowledge. And your first task is to kind of represent the real world constraints that you're trying to prove with an arithmetic circuit. You can use a library like Circom to specify the circuit in a high level language, and then it will be compiled down for you. Once you have that, that can go into a trusted setup ceremony that Tam also covered in the Solidity Fridays series, and I highly recommend looking at it. As a result of the ceremony, you'll get a common reference string, and you'll get a proving key and a validation key. So with your proving key, you can you can call something like snark.js, which has a really good implementation of proof generation algorithms like Groth16. And you want to provide your inputs, private inputs that you're hiding, the witness that will satisfy your circuit, that kind of proves that you know what you know. And then snark.js will kind of create a proof. A note about this is that proof generation is very computationally expensive, and it usually requires a centralized server, and it takes up a lot of memory and stuff like that. Once your proof is generated, you can submit your proof to a verifier. Could be any verifier, but it could also be a verifier on chain. So we'll look at some Solidity contracts that can take a proof and verify that it is a valid proof of the circuit. And to run the verification, you also need a validation key. And I believe, yes, a bunch of aspects of verification can also run in the browser. Tam, do you have any?
Awesome. No, I think that's great. Thanks. That's a great way to sum it up. And so
that's
I prefer the Solidity verifier. It's nice to have an on-chain element. But yeah, an important thing to note is that that server with the ZK snark proof and the snark.js and stuff is usually done off-chain because obviously it needs to be a bit private. So a zero-knowledge application is a combination of an on-chain and an off-chain application, if it is on-chain. But if it is on-chain, it can never just wholly be on-chain. It has to have off-chain aspects.
Right, and it's just so computationally expensive that I don't think proof generation will ever be on-chain. But I'm curious to see how, like, what ways we can decentralize it a bit more.
Yes,
yeah.
that's a good note, and we'll touch on that later, maybe. Yeah.
We'll keep this picture in mind as we look through this one specific project. So there is an indie developer called Melon Birdwatch, and this is based on his repo called Wordlines, which is an adaptation of this New York Times puzzle called Letterboxed. So I think we have to introduce the puzzle a bit before we can look into the architecture of this ZK game. So in order to play this game, you get this figure every day, and you need to join these letters to create valid English words. Your letters should be minimum of 3 letters. Your words should be minimum of 3 letters, and you need to combine letters from like orthogonal sides of the box. You can't like use consecutive letters on the same side. And it's a pretty hard constraint is that all the words you find have to be joined such that the last letter of a word becomes the first letter of the next word. So it's a very difficult game. And when you have a game like this and there's a new edition every day, you can spend a lot of effort solving it. And when you solve it, you feel a sense of accomplishment. We saw this with Wordle, that people would solve their Wordles and then send the screenshots to their friends. And the friends would be angry that they'd ruined the Wordle for them. So it's something like this. It can be useful to be able to prove that you've solved the puzzle without giving away the solution. So it's a natural fit for a ZK app. So the first task for the developer is to figure out how to represent these real-world constraints, so to speak, as in a form that will be amenable to be converted into an arithmetic circuit. So just to be more specific, in this case, this figure would be represented as this 2D array, and the solution would be this like vector of all the words that you found. And so in the circuit that was designed for this app, the line is like your solution to the puzzle. Figure is an encoding of the day's figure. And then you need to provide a dictionary, which is like all the valid words that can be created from this figure. Of course, you also give your private address, and for some reason, they're duplicated in this implementation, which we might uncover later. So the first challenge is like, how do you even, these English words are very hard to compute on. So the author came up with this really clever way of representing them, finding this like 32 base representation and using a rolling hash to find really compressed and unique integer representation of each word.
That's really cool.
Yeah. And so they had to do that for the dictionary as well. But it turned out that the dictionary was so big that they needed to find another representation, which is called a compressed dictionary. And then there's a bunch of stuff in the code which like decompresses this dictionary to actually do the lookup when the proof is sort of a lookup circuit to enforce the constraint that the word you find is in fact a valid word in the dictionary. So prefix sums are used for searching and like pattern matching. I think this technique, like this kind of integer representation, is often used in string search over large documents. So just as an aside. So we can look at the repo itself, and then there's an example of a figure and this like long dictionary of valid words. And here is sort of the arithmetic representation. So the entire figure can be represented in a very compressed way. And then these are the dictionary words. Similarly, here's a sample input, which includes the line, right? These are all the valid words that, or these are all the words in my solution. Here's the figure and here's the dictionary. So we need a circuit that can enforce a few constraints, right? It can make sure that every word belongs to the dictionary. It needs to make sure that each word, like the last letter is the first letter of the next word, and also needs to make sure that all letters of the figure are covered at least once. So I found the simplest circuit was really for figuring out whether a word belongs to the dictionary. So this was, maybe it'd be good to look at generally how these circuits are in the code. So here's the, I think part of the circuit. I think this circuit kind of does the dictionary extraction, and this is like, this checks whether a word is in the dictionary. And this circuit itself is made up of several smaller circuits, and an array of circuits actually, that I tried to visually represent. So, I mean, circum is mostly a familiar syntax. There's not a lot of very exotic elements other than this operator, which kind of is like, it's kind of like a require, where it enforces like this equality must be true. And it's also an assignment. It's like assigning these wires together. But visually, this in dictionary circuit that checks whether a word is in the dictionary or not is made up of an array of these two smaller circuits that are found in the circum library that have been implemented for you. So it might even be interesting to look at those if circum library is available here, which it's not. Do you think I should look online? It's very interesting to look at like how even such.
Yeah, I think that would be awesome.
Okay, let me use
show off circum a bit.
Sorry. Circumlib. So yes, in circumlib there are comparators, and so if you want to prove that an input is 0, you need to run this circuit, which has this intermediate signal called inverse, I'm supposing. And it checks that, yes, if input is not equal to 0, 1 over input or 0. God, so you really have to get into rudimentary arithmetic on a field. Maybe is equal is simple. Is equal is God. So is equal is built on is 0. And your input are like is an array of two signals, right, that you want to know are equal. And then you have like a subcomponent. Component is like a specific circuit. And you're making sure that in 1 minus in 0 is basically satisfies this circuit is 0. So like the difference between the two inputs is 0. So this is kind of the arithmetic thinking that is required if you're going this route. So they have an implementation of less than, less or equal, greater than. Surprisingly, the OR function is not here. This OR. It's in the node modules.
Oh, that makes sense. This must be a hard hat.
Yeah. All right. So you got the sense of that. So basically, they're calling is equal. They're looping through the dictionary, and the words in your line, the solution you submitted, and running is equal, and the output of that is being fed into this other circuit called in prefix, which I think checks whether the last letter or the next letter constraint is satisfied. And so this is an interesting way to make use of these circuits, because the output of this one is going into the next computation, like the next kind of circuit.
Oh, yeah, the one depends on the other.
Yeah, so it's like the sequential logic situation. And here we can see the loops. So the circuits are sort of declared here, right? In prefix is this, like, it's not even one circuit, it's an array of circuits. I don't know if that's a valid thing to say, but that's what intuitively it seems like. So these two, like, arrays of circuits are declared here. And then they loop over the dictionary to then instantiate, like, specific instances of the circuits, or sorry, really declare, like, specific circuits that all, like, stack up, right, to create the whole mega circuit. And then this is the actual loop where the signals are instantiated. So for that is equal circuit, the input is assigned to be the word, and the other input is assigned to be that word in the dictionary. So these are just assignments of signals. And then because these circuits are already declared, right, in the circumlib, they will just run, like you're specifying this sequential logic. And once this compiles, I think, like, data just flows through and it satisfies your constraints or not. So it's if people have done, like, digital systems design or Verilog, it's helpful. It's slightly familiar, at least that's how it feels to me. Otherwise it would be
okay, yeah, that makes sense.
Because you're not,
I can see the similarity.
Yeah. So this was the most agreeable function for me. Tam, do you have any thoughts?
No, nothing to add here. Okay, so this is the words.circom.
Yeah, I actually don't. The circuit.circom.
Oh, let's check this out maybe.
Yeah, so I think this
this takes words and lines.circom, so perhaps we go to lines first.
So lines, I think, is continual, seems to be checking whether your solution has those qualities of last character, next character. Yeah, I think that's the only sort of circuit it has, is the continuity check. And words has a bunch, right? So there's a bunch of stuff with padding, because they're edge cases. Words are different lengths. Yeah.
Extract last character. So you take that, and then there's probably also an extract first character, and then they do an is equal on those.
Yeah, character extractor and check figure.
That's probably just to check if the figure itself is valid, the starting input of the puzzle, perhaps.
No, it could be whether. You also need to check that all the, like, your solution covers all the letters in the figure. So it might be that. Do I have? Yes.
Oh, there you do.
Yeah. But it's a pretty it's making use of a lot of indices. So these are kind of like three-dimensional circuits, if I can call them. So our values equal. So it basically loops over your figure, loops over the line, and then each letter of the word. And then I think it just probably checks that they all exist in figure.
They're all included, yeah.
Yeah, but this is all put together in this circuit.circom, which is the mega circuit.
Yeah, and almost I mean, this is in every ZK application, basically. It might not be in Circom necessarily, but there'll be a circuit, the main circuit. And this is this application's main circuit.
So when you compile, probably this is what will become like circuit.wasm that you will input your like proof generation. I even have like a prototypical call to proof generation here. So this is like if you're writing a server, right, and you have a generate proof endpoint, and you're calling snark.js, you're calling got16 full proof, then you have to include like the compiled version of the circuit and the like proving key that proving key that was part of your trusted setup. That was the output of trusted setup ceremony and input. And then you get the generated proof. So here we are in the mega circuit, and lots of components are being declared. So I think extractor is what the thing that like it changes the representation of the
yes, okay.
Yeah, makes it make all of them the same representation so they can be checked. So you check figure, and then figure checker is called on all letters of the figure, it seems. And there's some padding check. There's some like it would be interesting to draw out this whole sort of big circuit to see how they come together, because it's definitely not trivial. There's a lot of I think branching paths in the circuit.
And nested areas. I know you like to draw out your circuits to help like understand them, and that's maybe a nice tip for viewers. Like I usually just read them and try and make sense of it in my head, but you draw it out and then you can actually follow the logic. So I'm gonna start doing that.
Does it work for you to read them?
Barely.
Okay. Yeah,
I struggle,
maybe it's digital design classes I was forced to take. We would always draw. And another like insight I have from that world is like it's really, and this is one of the limitations of ZK, is that it's really, you can build these elaborate labyrinths of logic, right? But how do you know? And they can be internally consistent, but how do you know that this is actually enforcing the real world constraints that
we were talking the other day and saying like you don't know that the circuit does do the real world constraints, and maybe there should be a library developed by people who takes in a circuit and then puts out the output of what it's actually checking and like shows you what the input would be, like a reverse Circom compiler.
Yeah, I think there's like definitely room for a good testing suite, because most of these repos, they don't seem to include testing that I can run or check. So I'd have to like do a lot of work to check that. And also like it'd be interesting to look into like formal verification and what those people have to offer for something like this. Because even if you have run a full testing suite with something like this, I think anything short of formal verification, I wouldn't be really deeply secure. I think that's it's like an intellectual vulnerability. Like the human brain is, I don't think, particularly suited to this work. But here we have the mega circuit, which we have not drawn out, but is like an exercise left for the reader. And I don't know what this is. Like main is being called on these. Oh, these are all the sizes, right? These it's declared here, and now it's being called, so to speak, and its only inputs are these sizes of all these arrays.
Okay.
Your dictionary size will actually change with each puzzle.
Yes.
Right.
That's an interesting one as well. Like how do you make the dictionary for each
Yeah,
puzzle?
they have
I would probably just write a Python script for that.
Yes, that's what they did. There is a Python script. I don't know if it's in the
maybe
word line generator. Oh, this is a puzzle generator. But I think this would include
yeah, you can't have a puzzle without doing the dictionary. So maybe
dictionary size. So this is probably
I miss Python actually.
yeah. So I think this is giving out the dictionary and also compressing it. So that's useful. Actually, that'd be interesting to see how the algorithms run. So a lot of good code here that
Sorry, who did you say made this code again? What's his name?
Yes. This is Nalin or Nibnalin on nibnalin.me. Yeah, we can add a link to the screencast or something. And this is a group of, I think this repo is just Nalin's work, but it's a group of people who've been collaborating and funded by 0xPark, which is applied ZK research institution.
I did one
So
of their Pyro courses, and they're really cool.
Yeah. So where are we going next? We are.
I think.
Okay.
Maybe perhaps we go back to the slides and
yeah. Oh yeah. One thing I wanted to find is like, how does minting work? So basically, idea of the ZK app is once you have solved the puzzle, you generate the proof, you submit the proof. If your proof is accepted, then you're able to mint an NFT, right? Proving that you've solved. But this was implemented in iOS, so I'm not finding the usual mint functions.
Oh gosh, it's Swift.
Yeah. So ETH raw transaction, get proof data, and pi A, pi B. These are all the proof things, right? These are. Is there a word for this? For these pies? Just proof is just always. In the nomenclature, it's usually pi, right?
Yes, I don't know if there's a word for it, but pi represents a proof.
So you got your proof, and there's your inputs, and so you're calling mint item in the contract, and providing just these four, inputs, creating transaction. Yeah, so pretty standard there. Well, it'd be good to find this contract, look at this mint item.
It might be in there
Later.
Just ignore.
Do you think we can? Okay. It's the contract address. What's the fastest way to look at the functions of this contract? Tam?
I don't actually know. Maybe we just scroll.
Oh no, but I don't think it's here, right? I don't think it's provided.
Oh yes.
Like you have to go to the blockchain, but that's for later then.
We could actually. I would be interested in it if you don't mind. What is it on? Is it on Etherscan? Yeah, cool. So it's
I
an
hope
Ethereum
so.
application.
Well,
they did say send ETH earlier, so it's probably.
Okay.
Let's see. Fingers crossed.
There are no matching entries. Am I doing something?
So perhaps it's on Polygon Scan or something. No, that's correct. That's how it's done. Interesting. I'm gonna actually open up this project's README quickly and.
Yeah.
Okay, cool. Let's see.
This would have been. on test flight.
Oh, there you go.
Why is the smart contract not in the...
That's very weird. It's not the first thing I've seen where they put their smart contract in their git ignore.
Yeah, like, well...
Oh, that's not there though.
But I couldn't...
Why they did this?
It's not in the client, it's not in the server, it's not...
Let's check there.
Wait.
Let's go highlight.
Oh.
Contracts.
Why is it not... Oh my god.
Oh, there's the verify as well.
Yeah. Why was this not in my... So word lines verifier, right?
Nice.
Is sensitive or not?
It must be, I guess.
Okay.
Just got it. Yeah.
Packages. No, so I don't have it.
Oh, you don't have it.
Interesting.
How long ago did you pull this?
Like a week ago. My git ignore, I don't know. Okay, well, let's just look at it here.
We'll look at the verify later on, but maybe now we just look at how it gets the token.
Yeah, so this is a token, right? Oh, so it is interesting. It's verifier ERC.
Okay, so this zero knowledge application goes a little bit in an interesting order. And basically, imagine that diagram we had at the beginning.
Yeah.
The very last step, their output is the minted token.
Yes,
And they first take in the verifier, which is also on chain. And this inherits the verifier. So you first verify that someone did indeed solve it. The proof is correct. The circuit was generated aptly, and then you can mint the token. So maybe it does make sense to look at the verifier next, or maybe we look at some of the
look at the mint.
stuff.
This mint, right? It's taking, so this is your proof, right? And this is your input. And so there's a matching of the address. Okay, verify proof, right? So, okay, that's the main interesting function. And verify proof is probably in verifier, yeah?
Probably, yeah.
So yeah, for verifier, almost all repos we've seen are using this code by Christian Reitweisner.
Yeah, we looked at so many verifiers this week, and so many projects, and they're all using this, which I find a bit strange. I would just write my own verifier, but especially because it has this pairing library, it makes me feel like it's very like Dark Forest inspired, like it came out around that time. So it's like, I mean, it's
I feel like this dates Dark Forest, no?
Oh, it must, yes.
17.
It's just very similar to the verifier that I read of Dark Forest earlier this
week.
Right,
because they probably used, they wrote it in this tradition. Right?
I wonder what else he's been up to since 2017. That could be a fun episode.
Yes. Okay, so there's a pairing library. It's always the same. We just want to see verify proof function. What is it calling? Yes, verifier. Using pairing, verifying key. Interesting. So verifying key is this very complicated object that uses the pairing library. And your proof also uses the pairing. Makes sense.
I see. Okay.
Yeah, so it's this mathematics field. Verify and verify proof. So verify proof probably calls verify. Yes.
There we go. Yeah.
So ABC. So first you... yes, you're putting them in proof. Oh, wow. And you have to like... Yeah, the pi, all the pi things from our proof are being sort of passed into this mathematics in this. Well, I guess they're very naturally. Okay, so then they become. Okay, well, we'll look at the pairing library again, but okay, let's see. So input values. Why is it doing that? Okay, then it calls verify. And what verify does is this, okay.
And we'll probably find that snark scalar field, if we put it into a prime round number verifier, would probably be prime.
Yeah. Compute the linear combination VKX and require that. Do you know why this is?
Yes. So we want our input to be within the field.
Yes.
It must be less than the field to be contained within.
Got it.
And that's why we usually choose a really big prime number as our field, and then we just
Yes.
only work with numbers smaller than that, and we make sure that all our maths, even our like if we did like a multiplication or an addition, we always do it modulo, because then we make sure we always stay within that field.
That makes sense. Yes, got it. Yeah. And that's why, yeah, that's what the pairing library I think does, is like it provides these valid operations in the field. So now you're adding VKX and multiplying VK.IC and yeah, just doing a bunch of mathematics on the field. So if God, what the fuck is pairing prod? Okay, I just want to check one last. Okay. Yeah, I want to check like what, like these, you know, like this VK alpha, beta, gamma, delta, VKIC. It'd be interesting to find out what these are. They're related to your verifying key somehow. But like, are they the same for every?
Yeah, I think they are when people use them. It's the same numbers. Maybe these are fields within which we do operations on the key. We make sure it's contained within those two fields.
Yeah.
What we could do is maybe if we go up to the
and this was also being called.
Yes, that is called later. Yeah.
So if you wanted to go up to.
Yeah, maybe we could look at his see his GitHub, and maybe there's a on this verifier. No, sorry, Christian.
Oh.
Yeah. Let's look at his GitHub, and then we can see this library, and maybe it has a nice README explaining the maths.
I believe this is the one, right? No, but this is also.
Oh, this is his. Yeah. That guy's also really legit.
Oh, look, this has better.
Oh, nice.
Yeah,
well, he uses elliptical curve cryptography as well.
Okay, where is Christian's?
Maybe he doesn't have GitHub. Maybe just say GitHub instead of verify.sol.
Yeah, I'll move that. Oh, this is
interesting. Hermes uses it too.
Annotated.
This is the Polygon one.
It seems like the product, right? And then the result of computing the pairing check. What is E? Pairing should return true. So convenience method for a pairing check for 2 pairs, pairing check for 4 pairs. So this pairing check is checking.
I think it's checking that the keys match, right?
Yeah, but what? Okay, let's see if this has any other comments. No. Who is Christian and why doesn't he have a GitHub? Oh. Yes. Maybe he has the verification here.
I feel like this is more the maths and theory behind it, but actually that is kind of what we want, just a very dense version of it.
At this point, we have reached the
there
point.
It is. We're on his, I think, so it's chriseth.github.io. Oh, wait, that's his, so it's chriseth.github.com. So I'm just going to check if.
Yeah. And I'm just
going to see if I can find it. you can look at that. I'm going to look at the, well, I found his GitHub finally.
Yeah.
How many contributions do you think he's done in the last year?
I don't know. It's 0.
4,908.
Holy
I've never
shit.
seen something like this. Wow. Okay, let's look around.
So this is very, I think this is useful because I think if the code had comments, the comments would have carried through its copies, right? So I think that this paper is probably the best.
This paper is probably the equivalent of a comment, but comments weren't enough.
Yes.
Because maths is so dense, so you wrote a paper. After the stream, could you please send this paper to me? I'd love to read it. Because this really is the verifier that everyone uses.
Yes. So how to evaluate a polynomial succinctly? So a group and generator G, and yes. And I think the E is just this kind of encryption. The verifier chooses a secret field element S and publishes secret field element S that is then encrypted based on the group. And so you just have a list of these that up to the maximum degree of polynomials. After that, S can be and has to be forgotten. This is what is called toxic waste.
Yes.
So using these values, the prover can compute EFS for arbitrary polynomials. Oh, actually, it's probably better to read the math. I feel so illuminated already. Not deeply, but just like, okay, polynomials. Okay, the problem is, the prover is computing E f of S for arbitrary polynomials f without knowing S. So if, for example, if we have 4x squared plus 2x plus 4, and then they're just doing it on S, which is sort of cast in this way based on the group generator, which is just this, which can be computed from the public common reference string without knowing S. So I don't know why that is the case, but I think for that we have to really understand what the common reference string is. I know it exists. I don't know what's in it, but so this is a proof. So to check,
well, this is almost the like the trusted setup ceremony.
This is the using the things from the trusted setup ceremony.
I see. Into the proof. Right? I see.
This is the proof generation, and now is the verification. So because F is destroyed, the verifier cannot check that the prover evaluated the polynomial correctly. For that, we choose another secret field element, alpha, and publish the following shifted values. So alpha is multiplied by another hidden S. And then, alpha is also destroyed. Okay, then this still the prover is computed. Yeah. So the prover establishes. Okay, so the prover is giving two things. This like the first equation and then the second one shifted by alpha. And then the verifier has to check that these values match. So I'm almost at the verge of understanding what the 3 pi's are, right? So this is probably one of the first ones, and this is the second one, or maybe it's like decomposed in this. And so the verifier does this by using a pairing function, E. The elliptic curve and the pairing function, so that the following property holds for all x, y. Okay, so the verifier is basically running a pairing function. The verifier checks that this pair holds, and this GA is known to the verifier because it's part of the CRS as common referencing. Actually, I'm You know, I took a group theory class in 2016, so I actually don't even remember what's the group. Okay, the generator, this index, all the elements of the group. So it's just an element of the group, right? It's like if I'm saying GA, this is just the 8th element of the group. I would believe. I will check this later. Okay, so it's part of the CRS. In order to see that this check is valid, let us look at these equalities. You cannot look at these equalities. Well, yes, I mean, A is just, we know A is this. This is what it was defined as. And when you have a group situation, you can do this. Yeah, so that's why they should be equal, right? These two. The important part is the question whether the prover can somehow come up with AB that fulfill the check, but not. The answer to this question is we hope not. What? This is called the D-power knowledge of exponent assumption. And it is unknown whether a cheating prover can do such a thing or not. What? So this whole thing is, I don't know. Why is this an unknown? I would like to check if it's still unknown. This seems like a vulnerability.
I'm gonna quickly check it out.
So, okay. Okay, the above protocol does not really allow the verifier to check that the prover evaluated. The verifier can only check that the prover evaluated some polynomial at point S. So the ZK snark for QSP will contain another value that allows the verifier to check that the prover did evaluate the correct polynomial. Okay, and so there's another protocol you have to follow. So now we know a bit about how a prover can compute the encrypted value of a polynomial. Okay. So this is very helpful actually. And we get some sense of how this works.
Thanks, so this has been really great.
Yeah, this is ZK snark in a nutshell.
Because this is what the verify that everyone uses is based on.
Yes,
so it's great. Yeah. Cool. Now we can check
out the. Now I know what all of them. I don't know why it works mathematically, but I know at least I know what is being paired and what. Yeah. Excellent. All right, I think we've used up plenty of our time. Do you want
we don't have too long left.
Thoughts and feelings?
The one thing we haven't touched on is Snox.js and its use. Also, here it's great that they use powers of tau in their setup ceremony because we actually covered that last week. Yeah, it's also not there, but maybe it is on GitHub.
There's another git ignore that ignores all of these. Right. Sorry. So, sorry, can you repeat what you were saying?
Sorry, I just want to see if the.
Do you want to see the
it's interesting because the powers of tau isn't there. It might be on GitHub, but if it's not, I just want to see what it is that they get ignored. What they call the file.
Sorry, the powers of tau was in
node server. Node? Sorry.
No, it was in packages, Circon.
Okay.
Okay, so there is this p tau. What is that? I'm trying to extract this. Oh God!
It could be an extension in Circom. So if I go circom.p tau, yeah, you don't have to download it.
Yeah.
Oh, cool. So in the Circom documentation, they do mention p tau. So it's let's just see. I'm just going to Control F. P tau. Okay. So. Yeah, actually, if you don't mind going to the Circom documentation, And then on the left, there's, and then this is actually the page I wanted to look at. So it uses Snarks.js.
Yes.
And you go in powers of tau, new.
This is a curve, elliptic curve.
Yes. Oh, yes. That is a type of elliptic curve. Yeah. And that's the one that powers of tau always uses, I think.
Yeah. So what is this
I don't
file?
know.
Oh, this is just, I guess this is the name of the file that you were using for the new ceremony.
And
And
then
then
that should be verbose.
First contribution. Contribute.
Okay, and now
they're all
we need
being
more than one
saved.
contributor.
Oh, so the new file it's incrementing for some reason. The circuit specific. So they would have had to run this. So this they would have used probably. And this they would have had to run. So this generates Z key file.
Yes, you in our initial diagram we saw this keys.
Oh, so look, I think this is the circuit, right? So you would have to put your circuit in as an input to GROT16 setup, right?
Yes.
And yes, your key is also an input. Wait, no. Which Z key is that? Ah, I see.
That's the initial Z key.
So phase 2, you contribute again. That's what that means. And then
but now Z key is passed
yeah.
in. So
yeah.
And
then to prove, you submit the key. And
the witness, very important.
Where do you, and like which step do you compute? Oh, computing the witness. Let's look at that. And like I thought you could just do this, but I guess, yeah, if you want to do it, if you want to verify on chain, you can't do this, but in the browser, you can just do this, right? You can.
Yes, I believe so.
You can just call Snark.js. Oh, verifying from a smart contract.
There we go. And then they say you can use the Solidity verifier.
What if everyone's code is being generated by this?
Oh yeah, like what if like Chris, his code is actually used by Circom?
I don't. That would be cool.
Maybe he works for Circom as well.
It does create a verify.sol file, but I think this might be a different file that we are not even seeing because it was git ignored. We are seeing word lines verified, like not verify.sol.
Yeah, that's the verify for the correctness of the puzzle, not the verify for the proof.
Yeah, this outputs Solidity code in a file name. Wait, but I mean, I'm sorry. Correctness of the puzzle. I mean, you verify the proof, right? To verify that you've solved the puzzle.
Well, we first have to verify that the puzzle is correct, and then we put that as the witness, I think, into the proof, and then we can verify that the proof is accurate proof.
Yes.
So that Circum verifier circuit, well, that circuit, not that Circum circuit, the word line verifier, I think, is verifying.
No, I think that actually it's the same file. Because look, it has pairing and verifier. So yes, actually all of the code is being generated by this function. And at least in that verifier.
We finally found it.
Yeah.
I feel like an archaeologist digging, and I just found some.
Yeah, that's why it's so poorly commented, because I feel like anyone who wrote that kind of code would like leave comments.
If I wrote anything like that, you don't have to comment. But if it's just a generate.
It's so easy then. Like what? Ugh, okay.
Maybe in a few episodes' time, we should make our own ZK app in an hour. Try like a very simple one.
We can make one. And what is it saying? The command takes validation key. You can take the code from this and paste it in Remix. Okay, just to look at the code, I guess. Generate.
It'll probably be that.
Is this generating the Solidity call?
It probably is. So it's Snarks making a call to the Solidity verifier.
Who developed Circum? Like, who are these people?
I don't know, but they have a GitHub. We could see who contributed. But yeah, I think
All right.
that might be us coming up on
Yes.
time, to be honest.
Yes.
Thank you. This has been very illuminating. I hope the viewers found
For
it
me
interesting.
too,
Yeah.
Thanks for having me. And
I'd love to have you again sometime and do some more zero knowledge stuff. Thanks for joining. I really appreciate it. I hope everyone has a good Friday.
Thank you for watching. See you later, Tam.
Thanks. This has been another episode of Solidity Fridays, brought to you by Linum Labs.